Welcome to the last Battlecode lecture of this year. We're going to talk about advanced pathing and navigation. A couple, or really just one announcement for today. There was a huge update to the visualizer last night. If you haven't seen that already, it's great. Smoother robot movements, nicer colors, better sprites for things, just all around better in every way. But all right, so navigation. Right now, what's implemented in Lecture Player is what some people call fuzzy nav, where you know the direction, the direction straight towards the target, which I've represented as X, but you're willing to deviate slightly if there are things in the way. So if you can go straight that way, you try it. If that's blocked, then you try slightly left. If that's blocked, you try slightly right. If that's blocked, you try straight left. If that's blocked, you try straight right. So that's what Lecture Player currently does. And so just as an example, or the way that I'm going to be showing these is these red things are impassable tiles. Maybe they're impassable because they're water. Maybe they're impassable because the elevation difference is too big, something like that. But they're impassable for some reason. And then the numbers are the turn that a robot is on, just so you can see like a robot's trail. So for example, this one, if we started this robot right here, this is where they start. Straight towards the target is where they'll be on the next turn. They can keep going straight, so that's where they'll be next time. Then they'll be there, and I'm keeping around the numbers just so that we can see sort of the path over time. So is that sort of notation clear? All right, great. So with fuzzy navigation, the way that this path would finish is the robot would go straight while it can. This is where it wants to go next, but that's blocked, so it'll try slightly left. That's not blocked. Great. Straight there, straight there, straight there, and then you're at the target. For this one, you're going straight there. Straight ahead is blocked, slightly left is not. So you can go here. Straight ahead is still blocked, slightly left is not. So you'd go here. Straight ahead, which I think diagonal is straight ahead, is blocked. So you'll try straight ahead, which is this one. That doesn't work. Slightly left, also blocked. Slightly right, also blocked. Straight left is not blocked, so that robot would go here. And then from here, straight ahead is this one, which is blocked. Slightly left is blocked. Slightly right is not blocked. Great, so the robot goes there, right? And then, straight ahead, blocked, left, slightly right, blocked, straight left, not blocked. Great, and it'll get stuck in that loop forever. This robot would go like this, and then straight ahead is blocked, slightly left is not, so you go here. Straight ahead is probably left here, so straight ahead is blocked, slightly left blocked, slightly right blocked, straight left not blocked, great, so go here. Straight ahead is blocked, slightly left is blocked, this one isn't blocked, great, so it'll go here, and this one will get stuck in a loop as well. So this is sort of an example of why fuzzy nav leaves you wanting sort of a better nav algorithm, because this obstacle is not even tricky, but it still gets stuck in at least two different places. So we can make a slight improvement to fuzzy nav just by not revisiting tiles that we've already been to. So no revisit nav is the same as fuzzy, but instead of giving up after straight left and straight right, we'll check all the directions, still in the best order. So you would first try, if this is the bot, or here, we'll do it over here. Yeah, if this is the bot, you would first, that's weird. If this is the bot, you would first try here, and then you'd try here, and then you'd try here. 4, 5, 6, 7, 8. So those are the directions you'd try. Instead of just 1 through 5, which is what fuzzy nav does. And also, you do not revisit tiles that you've already been to. So this one ends up the same way. It can successfully go here, 9, 10, and then you're at the target. But this one now, so they would go 5, 6, 7, 8, just like before. But this tile is now considered impassable. So I'm going to remove this one because it's a simple case if it's getting in the way. So this 7 is now considered impassable to this robot because it's already been there. So now straight ahead is here, slightly left, nope, slightly right, nope, all the way left, yes. And then the robot can get around the obstacle like that. So that's great. That's much better because we didn't revisit this tile that we'd already been to. For this one, it would be similar. So 7 here, 8 there, 9, and then 10 here. I'm going to remove this one so that it doesn't obfuscate us. I'm going to keep the 1s around just so that I can remember where I started. But so this bot is, we don't care about anymore. Okay, so this one goes 10 here, and before it would go back to 9, which is bad. And now, if straight ahead is this direction, slightly left, no, slightly right, no, all the way left, yes. So it'd go here, 12, and then make it around the obstacle like the previous one. So that's great. But realistically, you don't want to have an infinite, like you'll never step on a tile that you've ever stepped on. One, because maybe you want to go back to the same place multiple times. And two, because if you're checking every tile against a list of tiles that you visited or something like that, that could get expensive. So the situation in which this just fails, if you never go back, is in this case. So this robot would go here, straight ahead is this way, so slightly left, no, slightly right, yes, straight ahead, yes, straight ahead, no, slightly left, yes, and then it's, or whoops, we would want to put, oh, I needed that there. And then it gets stuck in this corner, and it can never escape. So if instead we only said, oh, well, you can't go anywhere you've been in the last 7 turns, then this would spend turn 9, turn 10, turn 11, right, all the way up to 14, and then it would go here, 15, and then 16, and now, and then this tile, 17, because, so when, sorry, that was too fast. Okay, so 16, straight ahead is probably here, maybe this way. All of these are blocked because they're less than 7 turns recent. The sides are blocked, and only this one, only back right and backwards is unblocked. But then once you're here, straight ahead is this way, blocked, not blocked, and you can make it around the obstacle like that. So that's one example in which if you don't have some threshold, it just totally fails because you could get trapped in a corner. But if the threshold is too low, then you can still get trapped on obstacles like this. So if we take this robot, it'll go 5, 6, 7 here, and then straight ahead is blocked, left blocked, right blocked, so we go left. Straight ahead is blocked, slightly left, slightly right, straight left, fine. Okay, straight ahead is blocked, slightly left, slightly right, slightly left, slightly right. No, so it'll go back into the left. So straight ahead is blocked, but right is unblocked, and then it'll keep going this way. Straight ahead is blocked, left is blocked, right is not blocked, so we'll go here. But then now straight ahead is here, blocked, because that's within 7. Slightly left, blocked, slightly right, blocked, left, blocked, but right, this is now 7 away, so this is a valid move, and we'll go here. And then straight ahead is blocked, but slightly left, oh, that's 7 away, so we'll go here, right? 7 away, we'll go here. And like, yes, I chose this so that it was exactly 7, but there are plenty of obstacles where, like, I just need to add a wall right here, and you'll be trapped forever, even with like 9 or 10, right? So that's the kind of problem you get stuck in if the threshold is too low, but if it's too high, then you could be trapped in this corner for however many turns the threshold is. So the the no revisits bug is really good, much better, like extremely simple to implement still. You just either need to keep a list of locations you visited, or you can have an array for the entire map, and then just remember which round you were at each tile. And if it was too recent, then you consider that an impassable tile. And it gets around pretty simple obstacles pretty easily. And like a good threshold is probably like 20 or 30, and that'll get you around really like even pretty big cup-shaped obstacles, at the expense of like occasionally getting stuck in corners like this. So this is a really solid, simple to implement navigation algorithm, which I'm a big fan of personally. Another very popular one is BugNav. So with BugNav uses a similar rule to, if you've ever heard the like maze solving rule, just keep your hand on the left wall and you'll eventually make it out. That's what BugNav does. So whenever BugNav can't make progress, it just follows the left wall until it can. So more precisely, you always remember the closest you've been to the target, and you always move closer if possible, regardless of walls or where you've been or whatever. But if you can't get closer to the target than the closest you've ever been, just follow the left wall. Follow the left wall until you get out from behind whatever it is. So in this example, this robot would go here. There is a closer tile that it can move to, so it just checks all the tiles. And this one is blocked, right? But this one is closer and unblocked, so it just goes there. Fine, closer, 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 success. So this one still works just the same. So that's great. I'm gonna get rid of that one. Okay, but what about this middle one? Or so then this one also. Well, I'll show you that one in a second. This middle one's a better example. Okay, so this one goes here. You can't get closer here, but either of these two locations works. So I'll go here, just assuming that we check left first. You could do it randomly if you wanted. It doesn't really matter. This one, you can still get closer, so we'll go here. But now you can't get any closer than 7. Going here would be slightly farther away. So now you go into bug mode. You remember 7 as this is the closest location that you've been, and then you keep your hand on the left wall. So 8 here. Is there any opportunity to go closer than you've already been? No. Stay on the left wall. 9 right there. Any opportunity to go closer? No. This spot that I'm on right now, this one, is the same distance as 7. So we go here to keep following the wall, and 7 is still our best. No opportunity to go closer than we've already been, which is 7. So we keep following the wall like that. And now there's an opportunity to go closer than we've ever been. So we take it, ignore the wall, and just keep going straight for the target. So great. We made it around this obstacle. It was slightly more than the no revisits nav, but really about the same. So this is pretty solid. It'll get you around. The obstacle just fine. Okay, so I'm going to delete that one, and we'll do another example. All right, so this one. If you happen, so you get here, and there are 2 places. Oh, and this is the closest place. So you do it, and that's it. You just make it around. Great. I'm going to put the good example back just for posterity here. But I wanted to continue with the 3 examples that we've been doing. Okay. So that's BugNav around a simple wall. Let's do the example that the no revisits nav failed on. So we'll do this one first. 4 would go here. You can go closer, so you go here. You can go closer, so you go here. You can go closer, so you go here. And now you can't get closer. So you put your left hand on the wall and you go here. And now you can get closer, so you just make it around like this. And you didn't even have to wait around for 7 turns to get stuck or to get unstuck. You just went straight around and followed the wall until you were closer than you were before. So that's great. That was a pretty easy one. Let's look at what happens with this one. So 5, 6, you can go closer here, you can go closer here, but now you can't go closer. So follow the wall on your left, go here, here, still can't get closer, still can't get closer, still can't get closer, still can't get closer. Looks like this one is this, yeah, not closer. So you keep following the left wall. You would go here, 16, following the left wall. And now you can finally get closer, and you stop following the wall and just go for it. So that's how that bug would resolve. The failure mode for bug nav is when you have to go around the entire map, which you may have seen some teams doing in the sprint tournament. It happened quite a bit. So here's the pathological case for bug nav. Say you've taken this route, now you can't get closer. So you follow the wall, and you follow the wall, and you keep following the wall, and you get all the way down here to like 25 or something, and you're still following the wall. It's like, I don't know, 30 maybe. You're still following the wall. This isn't closer than you were before. This is like 37. You're still following the wall down here at 42. You're still following the wall. Just for illustration's sake, you're still following. You follow the wall all the way up here to like 54 or 3 or something. And I think this is about where you get closer. But regardless, the way to go closer and the way to follow the wall are the same way. So you'll end up finally past this tiny little obstacle at 56, like 57, and then you finally made it around, right? Finally, and now you can just go straight for your target. Here, 61, 62, 63. 64. Oh, but now you can't move any closer. Better follow the left wall. So then you go 65, 66, and the numbers are so high that it's not even shading correctly anymore. Let's just put this here. So it's 64. Sorry, my conditional formatting apparently got lost somewhere in there. All right, anyways, so now you follow the wall all the way around again. Your 70 is up here, and then you like end up at 80 here, and then you go 80, 81, or 80, 81, 82. I just want to overwrite this old path a little bit so it's clear how bad of an idea this is. 84. Okay. So then you follow it all the way around again. You would end up all the way down here, following this wall. So this is going to be at like 130 or something, and then you are still bugging here. You still haven't even been closer, and then around like 145 or whatever it is, you finally get closer than you were before, and you make it at 147 or something like that, right? And this is terrible. These are two tiny little obstacles that you could have just like, if you had only chosen left, like just, I don't know, by a random chance or something, but you wouldn't be following the algorithm. And so that's why people end up going around the outside of the map, sometimes multiple times, in like the sprint tournament and stuff. So that's where bug can fail. But the advantage of bug is that it's pretty simple to implement. It's very, very computationally cheap, cheaper even than the no revisits one, because you don't even have to check if you've been there before. You just have to remember one tile, just the closest you've been. And if you're not closer than that, you follow the wall, and that's it. So very, very cheap computationally. Usually very solid. Like in this cup example that the no revisits one would have spent a lot of time bouncing back and forth in here. The bug just goes straight around it. So it's like really good for obstacles like that. But sometimes you go around the map. So one way to combat this is to like, if you're closer to one side of the map, then you follow the right wall. If you're closer to the other side, then you follow the left wall. And you just have to remember which side you're following. That'll save you from like some cases, but not all of them. Like you can still construct cases where it fails. But yeah, so this is BugNav. And yeah, this example makes fun of it, but BugNav is actually very solid. So like that's not a bad one to have. But there's another improvement, tangent bug. It's like bug, but you look a few steps in advance. So once you are close to an obstacle, so maybe you look 2 steps ahead. So right here, you say, okay, if I take one more step, I'm gonna not be able to move any closer. So what will I do in that case, right? If I take 2 more steps, I'm not gonna be able to move any closer. When I'm in that position, what am I going to do? Well, I'll try following the left wall. That would get me here, and then it would get me here, and then I don't know if I can see this tile or not. But if you can see this tile, then you can see, oh, that tile is maybe closer. I think it's closer. That tile might be closer. So this is like possibly an option. If I went to the left, I would follow the wall this way. I'd follow the wall this way, and then maybe I can see this tile, maybe I can't. But if you can't see it, so assuming that we have small vision, like only 3 tiles away, then you would follow it left, follow it right, and there's just wall in both directions. But at least you can skip a few steps. So if you don't think you can get around this obstacle necessarily, but you were going to follow the wall to the right, then you can preemptively go diagonally, which saves you 2 steps, right? Instead of going here, here, and then up like that. So that would have been 5, 6, 7 versus 5 and then 6. So that saves you 2 steps if you go straight for the corner. This is why it's called tangent. You take the line tangent to the edge of the obstacle that you can see. So instead of bugging straight for it and then straight along, you look where you would end up if you bugged at the end of your vision radius, which is like more computation than before, but still not that expensive, because it's not like you're doing breadth first search or like Dijkstra or something like that, or A-star. You just have to sort of simulate a few steps in your head, which is like step forward, step right, step right. And that's not too expensive, definitely more expensive, so you might not be able to look all the way to the end of the vision radius. But even if you look just two steps ahead or 3 steps ahead, then you can save a couple of steps by going in a tangent towards the edge of what you've explored. So if your bug says, oh, I'm going to end up here anyways, then you can just make a diagonal straight for there. And if you can see far enough, so like once you're at the 5, maybe you can even see that there's a way around the obstacle this way, but you can't see a way around on the bottom. So then you definitely know that you want to be going for this location, and you can step straight towards it and get around. So in the pathological example for bug, the way that this would look is you would have your tangent right here, and you see, okay, if I bug, I'm going to go here. So if I take a right, I'm going to end up here, and then I'll end up there. Okay, so at the very worst, I could shortcut here and then keep doing bug along the wall, and I've saved myself 3 steps. But what if I bugged to the right instead, or like bugged left instead? Then I would go here, here, and then I would go here, and then I would get closer than I was before. So that's even better, right? So this is the tangent that we're going to choose in this case, and you can go straight for that tangent, 3, 4, 5, like this. And because you looked ahead just a couple steps, like what if I chose like my left hand versus what if I chose my right hand? Sometimes you can see that one is better than the other, and you can choose that one and get around the obstacle much faster, often avoiding having to go around the entire map. Of course, if this was blocked like this, then the left and right directions don't look any better than each other. So maybe you'll just say, okay, if I bug, I'll end up here, and then here, and then here, and then there. Well, might as well save myself some time and just move straight there, right? And then you bug around the map, and you've saved 3 out of however many. But then when you get down here, you can say, oh, if I keep bugging, I'm going to end up right there. So I'll just skip that. So this was like 25 or something, right? So then you can just skip that and go, not 56, 26. You could skip that and go 26. And then you can say, oh, if I keep bugging like this, I'm going to end up right here. So I'll just go straight instead, 28, etc. And depending on how far you look ahead, you can skip a lot of corners and a lot of turns like this. So that's another advantage of having this like tangent addition to BugNav, where you look ahead a couple times and you go in the tangent to the edge of the obstacle that you can see. So again, back to how it was before. In the ideal case, you would end up doing something like 3, 4, if you can see far enough to get around like that. And then same thing when you reach this obstacle, you would say, okay, what if I bugged this way? Wow, that looks all right. If I bug this way, it does not look good. So I'll choose to keep my hand on the left this time instead of on the right. So that's tangent bug, sort of an addition. It adds a lot of complexity to BugNav. So often BugNav is just good enough and people don't do this. But if BugNav is failing you and you are sad about your robots running around the edge of the map, then go for it and implement tangent bug. Okay, great. So those are the main algorithms for like a single robot pathing around the map. Does anyone have any questions about those so far? Okay. There's one more that I want to talk about, which is sometimes if you have a lot of different robots going to the same destination a lot of times, it can be worth it to pre-compute where to go from every tile. So that's like a lot of work, but for something like your HQ or maybe evaporator or something like that, lots of robots are trying to go towards your HQ all the time. So it's worth it, it can be worth it to pre-compute from every tile how you should move to get to the HQ optimally. And this is an optimal algorithm. This is not an approximate, like, maybe if I follow the wall, then I'll get unstuck kind of algorithm. This will tell you like exactly where you should go from every tile to get to the HQ. But the cost is you have to compute all of that, and that can be expensive. And then also, like, if you can't see the entire map, then maybe some of this needs to be communicated to you by other robots on your team or the HQ or something like that. But the general way that it works is you just remember the number of steps away each tile is. So I've started out with 1s around the HQ. All of these are going to be 2s. 2. And then these are all 3s. And then we can go 4, 5, 6, 7 like this. There's going to be 4 and 4 here. We'll have 4s all like that. 5s here. 6s like that. And you always take the lowest number. So this is 5 according to coming from this direction, but it would actually be 8 coming from the other direction. So you'll always take the minimum. And in this case, since there's a 5 here, this one can be a 6. So these are all, that's a 5. And so these are 6s. And so you can have this nice sort of pattern where at every single location now, you can see sort of the best place to move is always in the direction of, sorry, the conditional formatting got lost again. So the best place to move is always the lowest number that you can see. So if you're on this tile, you just want to pick any of the 6s, and it doesn't even matter which 6 you pick. You just have to go on one of them, and then you'll be 6 steps away from the HQ. If you're on this tile, you could path around it this way if you just like were doing a regular pathing algorithm. But because we know that this way is 6 steps and this way is 4 steps, like you don't even need to care where the obstacles are. You just have to look around you and see, as long as the obstacles are infinity or something steps away, the lowest number is where you should go. So instead of having any ambiguity, when you get even to this location right here, this location, it looks like it would be faster to take a right, at least to me. But apparently it's not. The shortest path is actually to go here, and then to go here, and then this one, and then diagonally and like that. And so if you have this sort of pre-computed map of where to go, you can have an optimal path to from every location to a specific location. So again, not a general purpose algorithm. Oh wow, the math worked out really nicely with those 9s. Okay, anyways, not a general purpose algorithm, but it can tell you how to get to a single location optimally. I'm kind of ignoring the fact that the terrain can change, which I'll talk about some at the end. But just treating some tiles as impassable versus not impassable, this is kind of nice. So if you could somehow get this map to all of your units, then they would all know how to get to the HQ optimally. Or if this were the enemy HQ, maybe your drones are like scouting out the enemy HQ, and your drones can compute this map and like share it through the blockchain or something like that to the rest of your team. And then the landscaper backup can come in and optimally path to the enemy HQ. And it's like a very simple algorithm for an individual unit. Just choose the lowest number, and the complexity now is in generating this map. So how could you potentially go about doing that? So if we take this and imagine that you are just one robot and you don't have any map yet at all, or maybe the HQ has given you this map that says all of the 2s or something like that. But you come into existence in the world. Actually, say you don't even get anything. We'll start from scratch. Okay, so the miner comes into existence with no knowledge of the terrain or anything, and say they come into existence, I don't know, right here. So the current tile is 1 away from the HQ. It was just spawned. And let's just compute, so the miner is currently right here, so let's just compute all of the tiles that are adjacent to it. So this would be a 1, 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 and then the lowest number for this tile that it's adjacent to is a 2. So we could put a 2 there. And now we've started to make the beginnings of this map. The miner is still leaving the HQ, maybe looking for soup or something. So say that it moves here. Okay, let's compute them all again. So all of the new numbers for the adjacent tiles would be 3, 3, and 3. So that's fine. And then say the miner steps right here. So now we can compute, okay, this one, the things adjacent to this one must be a 2 because it has a 1 over here. This one must be a 3, and this one must be a 4. So the miner is right here. And then, okay, so now there's some obstacle. So maybe the miner goes here instead, and then we can compute these 2, 4 and 5 right there. So the miner's right here. Maybe it takes a step around the obstacle like that. We can compute the ones here, so this would be 4. And the way that I'm doing this is for each tile that we're trying to pre-compute, just look at all of its neighbors, and it's 1 more than the minimum, right? So if the miner's right here, 1 more than the minimum is 5, and then for these, it's all 6. And so the miner has taken more than 5 or 6 steps. Like, it didn't take an optimal path to this location, but when it wants to go back to the HQ, it knows the optimal path. So if the miner comes out here, maybe it takes a step onto this tile. This is a 7, 7, 7, whatever. And then maybe there's some soup right here or something. So it gets that soup, and then it needs to go back to the HQ. If it just ran a regular pathing algorithm, it might choose to go this way around the obstacle. It might choose to like bug around the edge of the screen or something. But because it's been building up this map on its way out from the HQ, it knows exactly where to go, which is the 6 and then the 5 and then straight back to the HQ. But if there were another miner that had happened to go this direction, so this miner has come over here and it knows that there's 4, 4 like this, 5, 5, 5. So that miner standing here just computed all those. And if that miner has communicated this to the other miners, then the miner that was just standing right here, instead of choosing the 6, would choose the 5. And so it's never even seen this part of the map. But because another miner has communicated to it that this tile's value is 5, that the miner that's over here can take that path. And similarly, if this miner over here tells everybody, oh, hey, this tile's a 7, and then the miner down here moves to this tile and checks it, and it's like, oh, actually, this tile's a 6, then all of the other miners know that whatever the minimum value is, that's the best we know of so far. So all the other miners will, instead of keeping around a 7 right here on this location, they'll know to update it to a 6. If the miner over here, if it happens in the other order, so like if the bottom miner sees this tile and says, okay, that's a 6, and then this miner comes over here as if we haven't seen it before. So this miner, the top miner is right here and says, oh, this tile looks like a 7 to me. Like everyone else can ignore that. And if this miner has seen the update from the other one, it knows that this one is actually just a 6. But it'll still tell everybody that these ones are 7s, at least, from standing right here. So that's great. So if you can get your miners to communicate with each other like this, they can build up a map nearby the HQ, or even for the whole map if they explore a lot, and sort of collaborate to fill in this picture of the minimum distance from every tile. And if you know the minimum distance from every tile, then you can find the optimal path back just by following the lowest numbers. So that's pretty cool. This is trickier with this year's game. So this is like a sort of a general purpose pathfinding algorithm. This is trickier with this year's game because the terrain is different and a tile may be impassable from some directions but not from other directions. So for this year in particular, I think this would be harder than it's worth. But it is a cool and interesting sort of different take on navigation, whereas all the other ones were like individual robots, doing their best. This one is sort of a collaborative and possibly optimal way to find paths to a single location. Yeah.
And would we be able to store the entire array in the blockchain as what kind of knockdown?
Yeah, so that's a great question. Okay, so the blockchain, you get 7 integers, right? So 7 integers, each is 32 bits. You're gonna have 7 times 32 for a single message. A single map location, so bits per transaction. A single map location can be 0 to 64 or 0 to 63, which is 2 to the 6th. So you need 6 bits for a single map location. 6 bits, or sorry, you need 2 times 6 bits map for the X and Y. So this is equals 6 times 2 for a single map location. So what that means is you can take this divided by this. You can express 18 map locations in a single message, but no information about the map locations. So if you also need to say, okay, what's the number of steps from the HQ from this map location? If we are going to have a small map, then we can say maybe 63 is a maximum. So we'll say we need an additional 6 bits of info per map location, num steps. So now you need this number divided by this number plus this number to send a full update. So this is updates, sort of tile updates per location, which is really good. Like 12 updates in a single message. Every turn you only see at most 8 new tiles doing just the adjacent thing that I was running, and most of those are duplicates anyways, so you don't need to resend them. So this way you could just wait until you have 12 new values to send those. The other miners can pick it up. Maybe the HQ can rebroadcast it from time to time from units that got spawned later so that they don't have to look through the whole blockchain. But you can send a lot of information in a single message if you tightly pack it together. So this isn't going to work if you use your 7 as X location, Y location number, X location, Y location number. That's only 2, right? So you have to do a lot of tricks where you pack multiple numbers into one integer, which I guess I could talk about some. But just taking that as something that's possible. You can send a ton of information per message. So this is actually not infeasible, except for the elevation thing. I mean, that doesn't make it infeasible, that just makes it harder. Plus, you have a lot of buildings that sit around and do nothing most of the time. So, and those buildings like have a decent vision radius. So if those buildings were just sitting around computing things like this, maybe that's a good way to handle an ever-changing map, where sometimes tiles can get closer and farther based on like landscapers digging holes or like filling in gaps or something like that. You could be using your buildings to make sure that this is up to date and to like rebroadcast it from time to time and stuff like that. But yeah, so this can be really powerful, especially with a lot of units that have a lot of extra compute just sitting around, scattered around the map potentially. But and then miners or like other units that are also exploring, and in particular drones, because they can go straight to the target location just flying, and then figure out the best way for a land unit to get there, and broadcast it back. So this could be really powerful if you can get the right sort of communications infrastructure in place. But yeah, so this is just another sort of interesting way to find paths. I think that's actually pretty much it. These are the main algorithms that I wanted to talk about. Does anyone have any questions about that? Oh, yeah.
These kind of algorithms, how do they work with like movable barriers? Like if there's other robots versus if there's like houses?
Right, so that's a great question. So the question was, what if a tile is impassable because a robot is in the way? And the answer is, it's up to you. So some people, in the past, my team has treated just robots as like immovable objects. And so we would get problems where like there would be two units following each other, and they would be completely like they'd be following each other along like the edge of the map or something, and it would be completely open, like there's nothing in the way. But if the back one moves first, then it'll just start bugging around the entire map because it saw the one in front of it as like an obstacle and was like, oh, better keep my left hand on the wall, and just like got lost, right? So that's a problem if you treat robots as immovable. Is like you could path around something that's going to move the next turn. So that's one problem. That's why one of the reasons that like fuzzy nav happens to work really well is because like if the robot's here this turn, then like you'll just move somewhere a little bit randomly in the nearby area, and then hopefully it moves also, and then you can keep going forward. So like fuzzy is ideal if you're trying to navigate through a clump of robots, because you always just kind of want to move forward, and if you can't move forward, then like just wait and someone else will move, and then you can keep going. No revisits is so that's the reason. So the no revisits one, this seems like kind of an evil map setup, right? Like why would the devs put walls like this just to trap your units in? Well, maybe these walls are actually units. Right, so maybe when you were in this position, there just happened to be a landscaper right here, and so you couldn't go around it. So you went like this, and then you got stuck in here because like this landscaper is also trying to path through you or something, and then like maybe there's a miner there, and like this is an actual wall, and so like this is like a much more reasonable kind of map shape, right? Just like a little bit of a jagged cliff kind of thing, but because you had other units also trying to go to the same place, they like got in each other's way, and you can sort of like get trapped in holes like that. And then same thing with here. Like if you just happen to have a unit standing right here, then like, oh, you bounce off that wall and you have to go all the way back over, all the way back, and like maybe you stay trapped forever, right? So that's one of the problems that you can run into treating units as walls. And that's how some of these situations can happen. Generally, from left to right is how much other units can get in your way. So with fuzzy nav, other units like don't really bother you. You just move when you can, and you don't move when you can't. But of course, you'll get stuck on actual immovable things. For no revisits, it's pretty similar to fuzzy. Like you just move when you can, and if you can't, then like fine, maybe you'll end up there again in 7 turns or whatever your threshold is. But you'll never sort of there isn't a long tail of like, there's a certain configuration that could get you stuck running around the entire map, for example, right? So there's like sort of less variance with these ones. With bug, it's pretty easy to just like get trapped into starting a loop. So for example, like if there isn't even a wall here, they're just like a bunch of miners like mining some soup, right? Maybe they'll be done in 2 turns, right? But because they were standing here when you happened to want to go this way, so like there's soup here. Just because they're standing here when you happen to want to go that way, you now bug around the entire map, and then like by the time you get over here, these miners are long gone, and like you could have just waited 2 turns, right? Or like tried to run into them twice and you know been fuzzily fumbling around with the barrier until they get out of the way. So bug nav can have sort of a higher variance if you treat units as obstacles. I think a lot of people end up doing something sort of hybrid, where if there's another unit in the way for too many turns, then you treat it as immovable. So in the example with miners right here, once your robot is right here, if it sees that it's obstructed by units, maybe move fuzzily. So like do fuzzy nav if you're blocked by units. But if it's walls, then they're not going to move anytime soon. So you should just do bug nav. Or like do fuzzy nav for like 5 turns, and if they're still in the way, then do bug nav or something like that. So yeah, that's a really good question, and that is a source of a lot of headaches because walls are much easier to path around because you know when they're going to move, which is never. Yeah. Any other questions? Someone else had one. Yeah.
I want to ask about how you would go about storing like multiple locations in like 1 and 0.
Yes, I would be happy to talk about that. Okay. If I say bit shifting, how many people are familiar with this word? How many people are unfamiliar? All right, great. You guys, wow, this is going to be such a good, okay. You're going to learn so many things. Okay. So numbers are ultimately stored as binary, right? So stop thinking of them in base 10 and start thinking of them as zeros and ones, right? A map location takes 12 bits, right? That's like you have a number that's 32 units long, and 12 of those you have to spend on a map location, 6 of those you have to spend on something else, right? So if your integer is, there's not a good way to show this. Okay, so I'll do it down here. Okay, so you have a certain number of bits, and you need 6 of them for the x location, for example. So if you have this one integer, this isn't 32 bits, but like pretend it's 32 bits. This is one integer. You want to store, say 7, and you know that the maximum this is going to be. We don't know, like the maximum is going to be 63, right? For a map location x. So this is x. Maybe y is 57. And then this is also max 63. So you want to store these 2 numbers. Instead of sending them as 2 integers, 32 bits has a max of a lot, like 2 to the 31 minus 1. So you don't want to necessarily store just one of these things when it can only go up to 63, right? So what you can do is you can take the first 6 bits. So I think this is 6. And 71 in binary, or 7 in binary, as a 6-bit number is 0, 0, 0. Am I off by 1? No, 1, 1, 1. I think 1 plus 2 plus so that's 7. 57 is this. Okay, that's not what I wanted. All 0. Okay, all ones except for that. Okay, is 1, 1, 1, 1, 1, 0, 0, 1. So instead of storing 7 like this, where this is all, so you could store, this is just empty, we'll call this empty int, just 7. So if you wanted to store just 7, it would look like this. And look at all that wasted space, right? 7, then 57, 1 map location. You could do it like this. So I'm just going to start from the left. So 7 is going to be the first 6 bits. 1, 1, 1. And then let me just do this so it's clear, the boundary. So that's 7. That's your X location. So no matter, it doesn't, like 7 I'm using as an example, but you could always put your X location in the first 6 bits, and then you could put your Y location in the next 6 bits. And so this is your Y location. And then, like, wow, look at all these, this isn't even a 32-bit integer, and look at all the space that we have left, right? We could put another 6-bit number in here. For example, the number of steps from the HQ, or something like that. So there's so much room. So much room. Okay, so there's so much room for so much information in a single integer. And before, it was all being wasted, right? Like, this is only something like 20. But in lecture player's code, there are things where you store 7 in 32 bits instead of 3 bits, which is what 7 takes, and 6 bits, which is the maximum it could possibly take, right? So there's so much room to play with a single integer that with when you know the bounds on like the map location or something else, you can really take advantage of that to pack them densely. And so the way you would do this in Java, let me just ripple it. I'll just show an interactive example. So I'm going to do it in Python. Or actually, I should do it in Java so that the syntax is the same. Create. So the way that you could do this is you could say, okay, so int packed message equals 0, right? So, and then we can say int x equals 7, as in our example, int y equals 57. So what you can do is, and I'm going to have to remember the syntax for Java, which is why I wanted to do it in Python. But if you wanted to pack these 2 integers into just one, then I think the way that you do it is packed message equals packed message. Oh yeah, I remember how to do this. Okay, so packed message. Packed message, this is the bit shifting operator. So what this does is it takes the bits of packed message and shifts them over 6. So before, packed message was all zeros. So we can take this. So this is our example that we're working. Packed message was all zeros. What this does is it takes all of it takes all of these except the last 6. It just drops the last 6. So it takes these ones. I know they're all zeros, so like it's the same thing, but it takes those particular zeros and puts them here, and then it fills these ones with new zeros. So this is important because we're about to overwrite everything to the left, or to the right of that line. So these lines are in the same place. So in between here, we shift left 6. Okay? So is everyone following that despite it all being zeros? Okay, great. So that's what that's going to do. And then, so we take this, and then we can just add x. So what is that? What? So, okay, so x is 1, 1, 1, 0, 0, 0, with the least significant bit on the right. So this is plus x. No, stop that. Plus x. And then we're going to get these 6, or not 6, these zeros, and I want a bar here. These zeros plus this sum, which, because we shifted, is guaranteed to be just x, right? So no matter what this initial number was, since we shifted it over 6, and x is never going to be more than 6, we know that this is always going to be zeros, so this sum right here is always going to be x. Or like these 6 bits at the end is always going to be x, if that makes sense. So let's go ahead and println. Bad. How do you? I think it's packed message dot to string 2. Nope, that's definitely wrong. Java print int as binary. 19 answers, amazing. Okay. 2 binary string. Oh, it's integer.toString. This is the one that I want. Okay. Great. So integer dot toString packed message 2. Okay, so let's see what happens here. So far we've only done x, but okay, great. It prints out hello world and then 111, which is exactly what we thought we were going to get, and it truncates all the extra zeros. So it's just printing these 3, but that's okay. We can work with that. So let's print out packed message before we start, so that we can just see, and then we do that, and then let's do the same thing but with the y. So packed message is going to shift over 6 again, and then we'll add y. So now what we expect to happen is we're going to take these zeros, except for the last 6, and we're going to take these numbers right here. Oh, actually, okay, to be clearer, we're going to take all of these, copy them, move them over 6. I'm going to add another little bar so that we can see, and then it's going to fill this with zeros. So this is another left shift by 6. And then we want to do plus y. So y was this. And again, because we know, like we've promised ourselves that y is never going to be more than 6 bits, so we know that the result of this is always going to be zeros because of the shift. Y is never going to be too long because we're not going to send a map location over 63. So this is going to get us exactly what we want, which is garbage over here, like we don't care about that. And then this is the encoding of x, and this is the encoding of y. But in one integer now instead of 2. So let's confirm that. Okay. So at first, it's probably going to be an empty string, or maybe 0. I don't know. I guess we'll see. Okay, yeah, so 0 first, and then 111, which is what we expect. Oh, and then this is printing it in... Oh yeah, so this is exactly what we thought. So, like we said, a ton of 1s, a couple zeros, and then 1. So it's not padding the zeros on the left, but this is, in fact, what I promised you we would get. So that's amazing. And there's so much room left in this integer. This is 12 digits, and integers are 32. So that's a pretty big deal. You can fit a lot of stuff in an integer. If we wanted to, we could add in something else, but like we could add in more information. But instead, let's talk about decoding. So like once you've packed this message, what do you do with it to get the original numbers back out, right? The answer is you can multiply. So this is a new bit trick. So shifting is the first thing that we talked about. Next, we're going to do a bitwise AND. So if we want to get the int original y, this one is easier because it's just the last 6 bits. So we can say packed message and, so this is, so in Java, and is logical, like true and false is false. Single and is bitwise and. So bitwise and, so we'll talk about decoding down here. Okay, decode. I'm going to take this. This is the encoded string, or the encoded message. So for decoding, to get y, so we'll just say and bitwise and with this particular magic string 11111 and 00000000000. Okay. So now if we take this and 0 and 1 is 0, right? So everything left of here is going to be zeros no matter what the encoded message is, which is exactly what we want. So everything left of that line is just guaranteed to be zeros because of how we set up this magic number. And then this one is going to be, since it's all ones, 1 and 1 is 1, and 1 and 0 is 0. So these 6 are just going to be these 6 bits, always. No matter what they are, it's always going to be the same. And so now we have x. Or y, whoops. So that's y, right? And we could do the same thing where we take this. I'm going to actually copy the whole block. So we could do the same exact thing, but instead of the ones right here, we could put them right here and put zeros right here. And then we'll get x, sort of, because so these will all be these will all be 0, and these will be exactly this. So now we have only the bits that used to be x, but they're in the wrong place, right? This number is 7 times 2 to the 6th, just not a valid application. So then what we need to do is right shift by 6. And then we take all of this, and it goes right here. And then the rest of these are zeros. So I'm going to add a little bar right here. These are the new zeros are on the left. And now we have x. Amazing. So if we did that in the actual code, we would take packed message and, for clarity, I'll specify it in the binary format. This is actually a valid way to write numbers in Java. So I'll just do a little, hold on, let's just make something up right here. We can say, or I'll do it down here to prove the point. So aside, if 0b111 equals 7 system.out.println bases are a social construct. Okay, so let's just check what that outputs. And while that's happening, original y. Okay. Oh, so bases are a social construct. This is exactly equal. Because so this is just like some nice syntax that Java lets you use to create binary numbers. There's also hex, so also 0x. 7 isn't very interesting because 7 is just, this is, and we can just say like 0x f equals 15 equals 0b, like that. So that's cool. Yeah. All right. Anyways, back to what we were doing. We are unpacking the message, so let's check that this gives us what we want. So we packed it all in. We're doing the and that I said right here. We're on this line. No, it's not magic, right? The point is that it's exactly 6 ones, which is the number of bits that we know that the number we want is. So lo and behold, we get 57 back. Okay, so what about original x? That one was trickier, right? So int original x equals, so packed message. The first thing we know we need to do. Well, actually, there's a shortcut. So notice that if we shifted first, so if we had shifted left 6 first, I'm just going to copy this whole thing and show you the opposite example. So if we had done it the opposite order, and we did this, then good. Actually, yeah, and then we can move this. Okay, so if we bit shift first, then we take these bits and we put them here, and we need a little bar so we can see where the zeros came from. Okay, and then there's zeros over here, so that's great. I don't want that one. Oh, and I don't. Okay, yeah. So this is x is this number right here now, but there's still this like garbage over here, right? So this is garbage. Okay, it's like we don't know what that is. We don't. Maybe it's not zeros, right? So we still have to do. I want this line here. Sorry. So we still have to do our bitwise and, but now we can just and with the same number as before. And this is 127, I think. Yes. No, this is 63. So bitwise and with 6 ones is the point. And so now we'll end up with x again, and with this bar doesn't matter anymore. So now we end up with x again. Amazing. And since that's easier than like, so there are 2 ways to do it. And one of them, the original way, was and with 0b 1 2 3 4 5 6 1 2 3 4 5 6, right? And then take this and left shift it 6. No, right shifted 6. Sorry, that's not left at all. Okay, so right. So we're doing that, and then we can print that out, and then I'll do it the better. It's not really better. It's just I like it better. The other possible way, which is original x alt. Whoops. I think underscores are allowed, right? Hopefully. Nope, that's a no. Original x alt. So this one will shift by 6 first, and then do our bitwise and with 0b 1 2 3 4 5 6. And this should be what we want. Amazing. So we've encoded, we've like packed the message tightly into a single integer, and then we've decoded it also. And these operations are super cheap. These are the cheapest operations that you can do. This is cheaper than addition. This is like, nothing is cheaper than bitwise operations. So it's actually like very, very inexpensive to tightly pack your messages. It just takes like some code and keeping everything straight. And again, you have to know the maximum value of everything, so you know how many bits to allocate to it. But it's very possible, and this is how to do it. I guess I'll just put this code in the This is a terrible way to share code, but I'm going to put it over here. Example code. Oh, that's even worse. No, hold on. Oh, that's also worse. Okay. I'll put the example code below so that there's a gigantic block and it's fine. Okay, example code. All right, and I'll share this sheet after lecture's over so that you can see all of this. And I'm gonna move it up some as well. But yeah, I'll reformat this a bit. But anyways, yeah.
So this, like, in your professional experience, have you seen like this level of trying to save space?
I have an open source Battlecode bot from when I was competing, and I'm very, very proud of the communications module, which does bitpacking like this in a very stupid way, because I didn't know about bit shifting at the time, so I was like multiplying things by powers of 2, which is equivalent of bit shifting, right? Like if I want to multiply something by 2 to the 6th, that's bit shifting it to the left to the 6th, or left 6 times. But I didn't know about that at the time, so I was multiplying by 2 to the 6th, which is very expensive and costs a lot of bytecode, so don't do it that way. But anyways, that is in a file somewhere. Where is it? Messagingcode.java. So I have all these different message types, all these different data types, like message reasons, and then like the amount of space that different data types take and stuff like that, and would just dynamically, like how much space data needs, and would dynamically pack things onto the end and split it across integers and stuff. And like this is the year we got second. And like I'm not gonna say it's all because of me and my communications, but it helped probably. But anyways, so like people do this in practice, not just my team. This is also bit operations like this is also a very, very, very common trick for making code run faster. So not even necessarily just like packing stuff into more integers, but if you are multiplying by a power of 2, don't do that. Just bit shift, and it's going to be so much faster. So, because like shifting it is like one instruction, and like just multiplying out the power of 2 is going to be like a couple of multiplications, and then multiplying it by the other thing is a multiplication, right? So that'll probably be, I don't know, at least like 7 or 10 instructions. Like there's probably intelligent things, or like intelligent optimizations, like maybe the compiler will pick that up or something. But like in real life code, using bit hacks is like very, very common to speed things up. And there's a lot of really cool tricks out there. If you want to learn about some of them, you should take 6172, which is all about making code run fast. But anyways, yeah, so that's, people do this, and it is a good idea despite being convoluted. So yeah, any other questions? Yeah.
You've mentioned Dijkstra's algorithm and A-star a couple times.
Yeah.
Could you elaborate a little bit on that? Because like, if you're trying to find like the enemy HQ and you've never been there before, you can't pre-compute stuff. So.
Right. Okay, so the question is, how do you get somewhere, like, so we've talked about like A-star and Dijkstra are like common search algorithms, right? For like finding the shortest path to something. And so like you can't do an optimal path unless you do the only optimal algorithm that I gave was the pre-computed one, which like you can't do if you don't know where the HQ is or don't know about the terrain in between it or whatever. And the answer is, you're right, but also in Battlecode you don't have enough bytecode to do A-star or Dijkstra or something like perfectly optimal, at least within your site radius. And so like that would be the ideal way to do it. If you knew the entire map and you weren't limited in computation, definitely A-star, very, very fast search algorithm. But you don't necessarily have either of those things for Battlecode. So that's why all of these algorithms, except the pre-computed one, rely only on your local information. And in fact, the fuzzy nav, no revisits, and bug nav never even look at any tile that isn't adjacent, right? It's like that local. You barely need to be able to see anything. You don't need to know anything about the rest of the map. You can run this algorithm and you will probably get there eventually. So
But I'm just curious what they are.
Oh.
Because I hear the terms.
Gotcha. Okay, so for an example like this, so BFS is if you start here, you check every path of length 1, and you see if you're at the destination. So you check all of these, and you're not at the destination. All right, so then you check, building on those paths that you know. You extend every path by 1, and you check every path of length 2. So you would make it out to this rectangle right here. And then if none of those are your destination, you check every path of length 4, which is out here. And then you check every path of length 5, every path of length 6, 7, all the way out. And then the first time that you encounter the target, that's the optimal path, right? Because you've always been checking the shortest possible path and you haven't seen it yet, right? Dijkstra's algorithm does that, but with a heap for choosing which path to extend. So with BFS, you just extend all the paths every time. With Dijkstra, so Dijkstra is really nice. It's basically the same when you have path lengths of 1, but if the costs, like the edge weights or whatever, like one step costs more than another, then Dijkstra is really nice because it uses a heap, which is a really cool data structure, to sort all of the paths by which one's the shortest, because you don't necessarily know which one's going to be the shortest at the next step when you have different edge costs. So that's Dijkstra. And then A star is a lot like Dijkstra, except you add a heuristic, where instead of just extending the shortest path, you extend the path that's like the one, so you have the path length plus a guess for how long it's going to be. And you always check the path with the shortest total between those two. And so it's important that your guess is always an underestimate, or it's never an overestimate, because if the path length is an overestimate, like say you're right here and you estimate that you're 100 tiles away, you might not check that path ever because it's so big, right? And you may find suboptimal path that like goes all the way out here and then comes back because that's less than 100. So you checked that before you checked the 100 one. So it's very, very common for, especially in a metric space, which is one where the triangle inequality holds, that you would use A star because you have a very, very natural heuristic, which is never an overestimate, which is the distance as the drone flies, right? So like if you went straight there and there were no obstacles, how far would it be? Obviously, that is not an overestimate. Often it's an underestimate, but that's fine. And that'll help A star like decide which paths to try next. Because if you're doing your BFS, you're still going to be checking paths that go all the way out here. But if your A star is telling you, hey, the distance from there to the minimum possible distance from there is really far. Like don't bother extending that path until we've exhausted all of our other options, right? That's why you use A star. And like A star is a really effective algorithm for search in practice. But not if you don't know the map and if you're resource constrained. So yeah.
Thank you.
You're welcome. Any other questions? This has been a good last lecture. All right. Well, then that is all I have to teach you.